Okay. Hi everyone. Today let's actually continue on with some more TensorStorm related AI work. So we're still in the process of learning how to use the ttnn Python library to be able to interface with the hardware. Just like another quick reminder here is that the ttnn is more like a library to just compute tensors. So when it comes to having the same feature set as Torch, it's really not the same type of thing. But we can do most of the work that we're interested in with ttnn. And it's also just kind of fun to think outside the box in terms of how we are able to translate some of the typical Torch things into ttnn. Again, most of this code is adapted from um, Sebastian Roschka's LLMs from Scratch repo. If you haven't read his Build an LLM from Scratch book, I highly recommend it. It's how I started learning how to build some of this LLM stuff, especially with GPT-2. Okay, so today we're going to take a step up and actually start writing an attention mechanism. And we're going to do a very basic one, just to kind of demonstrate the concepts and see if we can actually translate an attention mechanism written in Torch into using ttnn instead. So that's what we're going to be doing. So let's actually create another notebook. Oops. We should do Control Shift P, notebook, create new Jupyter notebook, and then let's just save that like right away. I'm going to save it under the notebooks and now save it as 05. Let's call it simple attention mechanism. So we're going to take our input embeddings and use that to help us compute the attention mechanism. So we're going to write a simple attention mechanism with our input embeddings. Our input embeddings are dimensions of like b times c times d, where b is the batch size, c is a dimension that represents the context length, and d is the embedding dimension. So that means like for every element in batch b, take that like as an input. We have some tensor in the context of C. Within C, we have basically D number of elements representing some embedding information. So it looks something like this. B times C times D. And then that's actually what we call this B is what we call the batch dimension. Okay. And then C, okay, let's just kind of do that, that. C is going to be the context dimension. And then we'll have a D that represents, in this case, the embedding dimension. So for like every single word or token, we have some sort of information encoded within that. And that's pretty much like attention in this case. Okay, I'm just so like tied up with this. Okay, so that didn't come out well. Let's actually turn that into a code block. Okay, so like the way to start that out is first let's just like understand what we actually need. So like to create like a very simple attention mechanism, we'll need to understand some of the terminology. So basically, we have a query, and the query is a vector given some token in context within the input embeddings tensor. we basically have some sort of corresponding, right, embeddings vector in that D dimension for that specific given token. We basically can like call this query q sub I, and I is the ith element inside that input embeddings tensor within that D dimension. And then we also have the attention score. And this one is actually the interesting one. It's the result of, like, in this case, in a very simple form, the dot product between like the query's embedding vector, so that tensor inside the dth dimension against like another token inside the same context. So we calculate basically all the attention scores for all the tokens in relative to that query, and the n number, right, like the last number of elements in the attention score vector, is the value that we have in the that corresponds to the cth dimension. Attention weight is just like taking the attention scores and then normalizing them. And then one thing to remember is that when we sum up all the attention weights within that entire context, all the elements should sum up to 1. And then the context vector is just the result of the matrix multiplication between the attention weights and then the input embeddings. And this is actually what we want to find out. So this is the attention, like the measurement of that attention. So yeah, it's kind of like a preview of what we need to do. I'm still learning all this myself, so shaky. So the first thing we need to do is we're going to create, well, we're going to write some code to, first of all, create a sample context, and then also import some libraries for Torch. So we'll just import Torch as usual. So just write some code here, import Torch, and then we'll say torch.manual seed. This is what Sebastian likes to do when he wants to create something reproducible. You just basically set a seed for any random generation, so that we'll always get more or less the same result. I should probably select the kernel. There we go, virtual environment. Okay. And then we're going to create sample context, basically a sentence, right, that we want to compute. And I'll explain how that structure looks like. So we'll define some context, and we'll say torch.tensor to create a torch tensor here. Let me make this bigger. Can't tell if my screen is big enough, but okay. So we'll have a torch.tensor, and then we're going to define some numbers. So basically, this is the batch dimension. So B, right? We only have one input batch, and then each one of these is going to be basically a token, right? So that's the context dimension. And we're going to have 6 of these. So we're going to have 6 tokens. We have 1, 2, 3, 4, 5, 6. So this is dimension B. This one's going to be dimension C. Okay. And then within that, we're going to have a dimension D. So in this case, it's dimension D. Okay. Maybe I should do this. Oops. B, and then we'll have C. Okay. So that's how we actually represent our input in this case. So B, C, D. Now, we want to represent the phrase, your journey starts with 1 step. Okay, and that's 1, your journey, 2, starts, 3, with, 4, 1, 5, step 6. And so we're going to represent, like, in that dth dimension, the embedding numbers in there. So I'll just start typing up the numbers, and then I'll continue on. So we'll and also one thing to know is that the embeddings dimension again is like something that you just like pick and roll with. So in this case, we're gonna have a dimension 3. Oops, that's about to do this. Okay. So each one of these words will have uh, a list of numbers, basically a single vector. So just keep typing. Then we'll have 0.77, 0.25, 0.0. Then where is it? 0.22, 0.77. Wait, I skipped something. 0.43, 0.55. I missed one. There we go. And then I can just get rid of this one. Okay. Okay. 0.55, 0.57, 0.85, 0.64. And then this last one here will be 0.05, 0.80, 0.55. Okay, so this one is your, right? This one corresponds to your. This one corresponds to journey. This one corresponds to starts. Corresponds to with. This one corresponds with 1. And this one is step. Okay, so each token is given some sort of embedding vector here. And we basically want to calculate the relationship between all of these given some sort of token. So let's just execute that. Looks good. If we were to just output that, we have the same torch tensor here. Okay. So given like our context, for example, we want to compute like for like one token. Like let's take the second token, and that token corresponds to journey. We want to compute that context vector. Okay, so we'll basically first compute the attention scores, the attention weight, and then finally we get the context vector off from that information. So let me just kind of write that down. So compute a so then we'll basically call that a query, right? So selecting an item for query. So given our context, okay, we would like to compute for the second token the context vector for the token corresponding to the word journey. Okay, so your journey starts with 1 step. Okay, so this is the context vector is the attention. Okay, so how do we start with that? Well, basically, let's just create our query. Okay, so just do q sub second one, we'll just say q sub 2. Okay, and that's gonna be context at 1 because it's 0th index, and let's just output q2. So we get 0.55, 0.87, 0.66, and that's exactly the second one here. So your journey. Okay. Next, we want to compute the attention score. So we'll just add this, compute the attention score. So how we do that is basically, we say attention scores is going to be first, we're going to create an empty tensor with the length of the entire context. So in this case, what that would be if we were to output that, okay, is 6. Okay, so we have 1, 2, 3, 4, 5, 6. A context length of 6. Okay. So next, what we want to do is we want to take the dot product of each corresponding element in the basically the tensor that we found here, this Q2, dot product that with every tensor inside that context. So in this case, dot product with all of these guys here, right? Okay. And so what ends up happening is that we're going to get another tensor that comes out. And that's basically the attention score. Okay, so in order to simplify this, basically make it less confusing, I just basically rewrote it. This context to just contain like all the tokens, and then each one of them will contain the items for the embedding input. So yeah, so it'll just be a single input. Instead of I'm just gonna remove the batch dimension in this case. So then all that will just flatten down to basically one dimension less. So that makes it simple. And then we can just like dot product everything, right? So we can just say for I, we're gonna dot product every the query vector, which is q sub 2, with every single tensor in our context. So yeah, we'll just write a simple loop here. So for I and in the corresponding tensor sub I in enumerate. So we want to enumerate over our context. What we want to do is we're going to compute the attention scores for that specific token at that position, right, with the dot product. So attention scores at I is going to be torch dot Q2 T sub I, and then we can just T sub I, and we can just output that attention scores and see what happens. Okay, cool. So we get like a single vector in this case. Yeah. So you get 0.9346, 1.4950, 1.4750, and so on. So like this is basically the attention for every like given this word journey here. This is the attention score for the corresponding other tokens in those positions, right? Okay, so then right now we want to normalize that. We want it to eventually sum up like have all of them sum up to 1 in this case. So we need to normalize it, right? So normalize the attention scores and create the attention weights. Typo. Not my normal keyboard today. On my laptop. Okay. So, and then basically all elements in the attention weight vector should sum up to 1. Okay. So we can write the code for that. Basically, it's attention weights equals to torch dot softmax, right? So that's softmax is basically a helper that will take a tensor, given some tensor, and some dimension that you want it to like basically have all elements sum up to 1 against, right? So in this case, we want that last dimension. We want the since we have just basically 1 dimension here, right? If we do attention scores dot shape, right? We just basically have like that single dimension. We just want to get that last dimension. We can do that with -1. So attention scores dim -1. Okay, and then at this point, all of them should be normalized to the point where if we were to sum up everything here, it should be close to 1. And how we can do that is test by using the torch sum against that tensor. So sum the values inside the tensor. So let's do that. So it'll be attention weights dot sum, And then we see that actually now we know that attention weights is normalized because all values in that tensor sums up to 1. And we could think of them as like probabilities, right? Okay. So now we have the attention scores, we have the attention weights. Now we need to compute the context vector. So, okay. Okay, so we're going to compute the context vector. And again, we're working with the second token. And so what we want to do is we want to multiply like all the elements in the attention weights here, okay, against the elements in that corresponding position of the entire context. So like take this tensor here and uh, multiply that against basically the individual like tensors inside the context. So we'll multiply against this one, this one, this one, and so on. Okay. Then we actually sum it all up. We add to it, and then the final resulting tensor is the context vector. And that's really just for the second token journey. So we'll just write the code for that one query. And then we're going to generalize all that into basically entire matrix full of all the tokens inside the context. So it's basically creating another tensor, context vector, initialize everything to zeros, and then we're just going to get the length of q sub 2 because that's the context vector we want to compute for this specific token. And then we're going to iterate through basically every tensor inside the context again. Okay. Enumerate context and context vector plus equals attention weights. Okay. We want the attention weights, and we're going to multiply that by basically pointwise to the elements inside C sub I, which is going to be that corresponding context vector. And we just return that. Okay, so we get 0.4419, 0.6528, and then 0.5633. Okay, so we're able to get the context vector for one of these tokens. What we want now is to be able to generalize it for all of the tokens. So let's see, generalize context computation for all tokens in input. Okay. Ooh, that's big. Okay. So basically we just need to take the matrix multiplication of the tensor inside of all the context in its transposed form. So basically it's gonna be context I guess matrix multiply the context with the transpose of context. Basically it's like the same thing as performing like the dot product of a query, like given some query with the rest of the tokens inside the context. So basically what we can do is take attention scores again, and we just take the context, the input, then we're going to matrix multiply in torch against the transpose of that context. And then we'll get a bigger matrix this time. The format is similar, right, to as if we were computing one. So in this case, it's going to be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, which makes sense because given every token, you want to compute basically the attention scores for all the other corresponding tokens. You have 6 tokens to do that against, and then you're comparing it with 6 other tokens. So then now you'll have a 6 by 6 in this case. And then what we want to do is we want to take this matrix of attention scores, and then we want to normalize all that, right? And again, we can normalize with softmax here, right? So we can do that with just the softmax helper, just like before, the same thing. Because the torch is smart enough to recognize how to compute that given some shape. Because we want to just softmax against all the tensors on the last dimension. So again, it's going to be given the attention scores against the last dimension, and we'll see what that looks like. Okay, so yeah, each one of these should actually sum up to 1. So given every tensor here, right? And we should actually, if we were to sum it all up, it will equal to 1. And finally, we can get the context vector by taking the attention weights and doing that matrix multiplication against context, because that's what we were doing up here, right? We were just basically multiplying, given one of these attention weights against the individual context tensor or vector, what do you call it? Okay, so context vectors with S is going to be attention weights. Okay, matrix multiply with the input. And because that's, remember, this is basically the C sub I, this is basically the Q sub, well, not Q, attention weights, the individual elements in the attention weights. And then we'll see what that looks like. Okay, so we end up, again, so it's consistent. The dimensions is consistent because right here we ended up with 3, right? And this one we end up with 3. And notice how here, see the journey part of our context has the same values as what we computed manually up here. 4419, 6528, 5633, 4419, 6528, 5633. So just it's equivalent. Okay. So that's like the way to do it in Torch, right? So that's very simple attention. How we're going to do that now in ttnn is pretty much the same operations, right? So I think it's going to be helpful if we end up visualizing this too with our like tracer graph. So let's use that, and then let's translate all the simple computations into the ttnn library. So oops, I don't want to ask Copilot. Okay. Change that to Markdown. How do I change the Markdown? Didn't escape. How do I? No. Okay. There we go. All right. So we'll say simple attention mechanism in ttnn. Okay. Okay, so first things first, we want to set up the environment. So set up the environment, and we can just specify that as import OS. We want to turn on, or at least disable the enable fast runtime mode flag in our ttnn config override so that we can actually start tracing things, right? So we do os.environ ttnn config overrides. What we want to set this to is that JSON again. I'm going to manually type that JSON again. So it's going to be enable fast runtime mode, right? False. Okay. So that sets the environment variable, and I think we can just test that by doing os environ.get, right? ttnn config overrides to check, and it should be the right value. Okay, so next we need to import torch because we need that to convert back and forth between torch tensors to ttnn. Then we also need to import ttnn, and then we need to import the tracer stuff. Then we're going to redefine the context again, which is going to be used as input. I'm going to copy and paste that part. And we'll also use the same manual C. So import everything needed and define the input, sample input again. Okay. So it says easy as import torch, import ttnn, from ttnn.tracer, imports trace and visualize. Then we could do torch.manual seed. We'll set that to 1 through 3. And then I'm going to copy and paste all the way up here. Basically the same context because I don't want to type all that again. Okay. And then let's just see if we did it right. Okay, context. Cool. And let's just output the shape too. So we'll have this simple torch tensor that we're going to be using for ttnn stuff. Let's first convert that context to like the ttnn tensor. So we'll say we'll just type context ttnn dot from torch. We're going to pass in context, okay? And then D type has to be bfloat 16, and that's what the hardware natively supports. And then we're going to also pass that in as we're going to create this ttnn tensor in tile layout. Okay, so that just makes life much easier. Oh, we also want to do this. We want to turn on tracing, so we can do with trace. So we'll have the context ttnn, and we also need the transpose version for later because we need to do that matrix multiplication. So we do context transposed ttnn dot from torch. We want to just do context.t, take advantage of torch at this moment. B type is going to be, again, bfloat 16. And then the layout will be ttnn dot tile layout. Okay. All right, at this point, we could just visualize what's actually happening, like that graph that we saw earlier. So in a past notebook, so we just do visualize context ttnn, visualize context transpose ttnn, and basically here it is. So I think we can just kind of view it here. Yeah. So basically we created two tensors, right? One that is starts out as torch tensor 6x3. You can guess that is the tensor corresponding to our input. We turn that into a ttnn tensor. See how it starts out as a torch float 32 tensor, but then we change that into a bfloat 16 ttnn tensor with tile layout. Then we also created a transposed version. Basically, we permuted the dimensions here from 6.3 to 3.6. Again, it's float 32 as input using this from torch call. Then we turn that into a bfloat 16 tensor with tile layout. Okay, so far so good. Now, so at this point, we just needed that, right? We have everything set up to really just compute the context vectors, right? So again, so this is gonna be like it's like a dance, right? So we have to like take the context and the transpose context vectors, or not vectors, ttnn tensors, and then like transfer them to the device, the wormhole that we have. And then we have to compute those tensors using ttnn.matmul, which is the matrix multiplication. So we have the attention scores at that point, right? And since we've already like created those context and context transpose ttn tensors as tile layout, we don't have to do anything special. We just need to make sure they're in the device at that point. Okay, so once we have those attention scores, we need to perform a softmax on that resulting matrix. And then we need to also compute the context vectors with the result of that one, because that'll be the attention weights ttnn version. So we'll take that, compute the context vectors using a matrix multiplication against those attention weights, the normalized attention scores, and then the context that we have inside the wormhole at that moment. And then what we could do is we can just transfer those context vectors in ttnn form inside the hardware back to our host device, our computer, our CPU, as a torch tensor. So lots of steps. Let me write that down. So basically, one, transfer the context and transposed version of the context ttnn tensors to the device. Okay, so that's step one. Step two, compute the attention scores using ttnn.matmul. Okay, assume both the context and context transposed ttnn tensors are already in the device and in tile layout. Okay. Perform softmax on the resulting attention scores tensor. Okay. This was in step two. It was results in step two. Then finally, we need to, or not finally, we need to compute the context vectors using ttnn matmul against attention weights and context, right? Attention weights were normalized or are normalized attention scores. Okay. This is result from step 3. And then 5, transfer the results of step 4, the context vectors, back to CPU as torch tensors. Okay, that's going to be our process here. So, as always, we need to define the device ID, and then we need to open up the device with that device ID to grab the handle of the device. So we do device ID, it's going to be 0, so that's what we're going to define the device as. Get the handle to the device using ttnn.openDevice. Pass in the device ID. Let's just like write code to close the device right away. We don't want to leave it hanging, right? So ttnn.close device. Then pass in that handle right there. Oops. Okay. Okay. So, okay. So now we need to also wrap. We also need to wrap all these operations around with trace so that we can actually visualize things. So let's do that. So let's do with trace. Okay. Contexts ttnn. We need to send our current context ttnn tensor to the device. So ttnn.toDevice. We'll take our current context.ttnn, send it to the device that we found here by opening up the device. We'll do the same thing with the transpose version. Context transpose ttnn, ttnn.toDevice, context transpose ttnn device. Then we're going to compute the attention scores using the matmul against the context ttnn and the context transpose ttnn. So attention scores ttnn is going to be ttnn.matmul. So matrix multiplication against the context ttnn and the context transposed ttnn. And then we're going to get the attention weights by doing that a softmax on that. So ttnn.softmax, attention weights ttnn is ttnn.softmax against attention scores ttnn with dimensions -1, meaning the last dimension. And then finally, we compute the context vectors ttnn with another matrix multiplication, matmul, on the attention weights ttnn and the context ttnn. So everything's in hardware at this point, right? And then we want to now transfer that back to the host. So we'll say context vectors ttnn, or let's say torch. Okay. So we're going to first do ttnn dot to torch, ttnn dot from device. Actually, you know, I think we can just do to torch. I think that might just work. Context vectors ttnn. I think it automatically will transfer back to torch. So we do ttnn to torch. Does that require device? Let's see. To torch. Oh, optional. Defaults to none. We'll just add it. So we'll do device equals device, just in case, to be more explicit. So device equals device. Okay. At this point, what we can do is we can just at least close the device, right? And then output the torch version. Okay. So context vectors torch. And we'll see what we get from that. So here we go. Okay, cool. So notice how we get somewhat like similar results to the torch version relatively, right? So we look at this one. Maybe is it this one? Yeah, I think this one here. No, this is the input. Where are we? We gotta go further up. Here. So we take a look at this. Let's just copy the cell output. Okay. We take a look at that and then just turn that into Markdown. Okay. So we'll say this one's the torch version. And then we'll say this one is the ttnn version. Okay. Taking a look, we mostly see similar results, right? It should be right in that ballpark, you know, given that this is a float 32 and this is a B float 16, and there's like transferring from device back and forth, conversions. We do lose some stuff, but it's not that big of a deal. So yeah. So that's how we actually calculate in ttnn. Now let's actually visualize how that looked like the process in trying to get there with the graph. So we do visualize context vectors torch, and I think this is supposed to be code. Okay, there we go. And I think we should get this big graph here. Yeah. So let's see what we did to get there. So we created, again, this is the whole story, right? So we created context vectors and context vectors transposed. We basically used from torch to do that. We get outputs and then we pass them to device, right? We're sending them to our device. So it goes from bfloat 16 tile to bfloat 16 tile, but in DRAM memory. So the tensors at a certain point will then be sitting in DRAM for the wormhole. Then we're going to take, in this case, the context ttnn and the context ttnn transposed, right? And do a ttnn map mul on it to get, in this case now, both in hardware outcomes, attention scores in hardware. Okay, we perform the softmax against that, and we'll still get the same type of tensor, but they're normalized into attention weights. Okay. Then what we end up doing is we'll do a matrix multiplication against the attention weights here as the first input. And then remember our context ttnn here, right? That gets passed in as a second input. Out comes basically a context vectors ttnn. We convert that basically from bfloat 16 tile DRAM, basically in our wormhole hardware. We bring it back out as a torch bfloat 16 tensor. Okay, so yeah, that's basically the gist of it. That's like how you do simple attention in ttnn. So Let's just like build off from that and start doing more complicated things again. Yeah, I think that's it for now. See you guys next time.